In this work, we present bilateral guided radiance field processing. NeRF has achieved unprecedented performance in novel view synthesis. By exploring the cross-view consistency between input, it reconstructs a realistic-looking 3D volume like this. However, such consistency is not always guaranteed. This is mainly because each view is processed by the camera independently to enhance its visual quality. Such per-view enhancement may result in brightness or color inconsistency. As a result, this inconsistency leads to floaters in the rendering. To address this issue, we propose a novel method that disentangles per-view camera enhancements during the training stage. Compared to the baseline method, our approach can synthesize cleaner novel views. Furthermore, we also propose a 3D finishing pipeline. Given an edited single view shown on the right as a reference, our methods can also lift this 2D editing to the 3D space. Moreover, our radiance field finishing also applies to 360-degree scenes. The user can edit one view in 2D editor, and the algorithm can seamlessly propagate this editing through the entire scenes without introducing color distortions or flickering. Let us first look into the training stage. To disentangle the photometric variation, a principal way is to explicitly express the camera processing for each view. That is to say, the NeRF model will first output an image with average processing, then a view-dependent camera processing, or in other words, ISP, is applied to synthesize the final view. Since NeRF is a black box algorithm, we seek a differentiable ISP proxy that can jointly optimize with the NeRF. Here we use a classical bilateral grid as an IC proxy. Bilateral grid is a 3D array, and each cell stores a 12-dove affine transformation. To mimic ISP processing of each view, for each pixel, we first convert its RGB value to grayscale guidance. We then use the pixel coordinate and the guidance value to slice the bilateral grid. The slicing process is an interpolation of affine models stored in the 3D grid cells. After slicing, we obtain a 3x4 matrix that can transform the original RGB color to a new color with camera processing. Then, these bilateral grids that approximate the per-view processing will be jointly trained with NeRF renderer. Next, in the finishing stage, to upgrade 2D editing to 3D volume, we also propose a 3D ISP. For each input point x, the 3D ISP will transform the radiance color of the query point to a new color. After that, the volume renderer can render the radiance field with transformed new colors. To map the user-desired editing to the 3D space, we can anchor the camera to the viewpoint of the provided reference and optimize the 3D ISP to minimize the photometric distance between the rendering result and 2D editing reference. Since there's only a single view reference, the challenge is to seek a 3D ISP proxy that can be optimized to find color manipulations for the whole scene. Our solution is to use a low-rank 4D bilateral grid as the 3D XV proxy. First, a 4D bilateral grid is a simple extension of the image-level bilateral grid, but for processing 3D views. Second, we regularize the rank of the 4D bilateral grid to fill the unseen areas. Next, we present a comparison with the GLO-based method, which also handles photometric variation. In this low-light case, we find the affine GLO will introduce some artifacts to the results. In the dark sky, affine GLO introduces artifacts while modulating the noise, while our method renders clean images. We also note that the affine GLO may remove necessary view-dependent effect. In this case, it generates strange specular highlight on the down tube of the bike, while our methods preserve this interesting view-dependent effect shown on the left. Here's another case. As a practice for nighttime photography, it is usually necessary to adjust the brightness of the foreground and background. Our methods can achieve this on this 3D scene. After editing, we can see the prominence of foreground subject is enhanced. Here's another case. The user can adjust the saturations, hues, and the sky colors of this 3D scene. In this drone capture scene, we also show our methods can make a transition from daytime to dusk. Our method can also transform the appearance of a 3D scene to depict various weathers, like a snowy winter or a sunny autumn. In this last case, thanks for the added awareness of the Bilateral grid, our Radiance Field finishing also performs well in this local editing like this. Thanks for watching.